Hello, hello. What's up, everyone? Welcome to your first CS lesson here at Spirit University. I'm Aki LITE, your pocket programming pal. In this class, I'm going to start you guys off from literally zero. And maybe that's a bit of a lie because you're going to need 1, 2. But that's it. Just these two numbers. I promise. It may not look like much, but together these two make up the language of computers. Binary. And using these two numbers, you can pretty much represent anything you want with them. And computers do. So what we're going to do here today is learn how to think like a computer. Yes, this is a big goose egg. I can make it a little bit better. We can do a little bit better than that one. 0. Oh, I tried my best. And that's all that's important. Okay, so programming at its core is just us giving instructions to a computer, right? And to do that, it kind of helps us to know how computers make decisions. Now, computers are obviously very complex machines, but we can break it down to the simplest form. So how do we interact with a computer? This is a computer. Maybe a bit of an older model, but a computer nonetheless. Actually, let's give him a name. We'll call him Mr. Computer. Right? So we can give Mr. Computer some inputs. These can be anything we want. Like I can give him eggs, give him milk, and maybe some flour, and some chocolate. Why not? So these are all inputs. So they're things that we're giving Mr. Computer. And Mr. Computer has a set of instruction manuals. And using these instruction manuals, he can actually use our inputs to do something, right? So he reads them and then he'll give us a different set of outputs. He can give us cookies or muffin, maybe even like a cake. But yeah, it really depends on whatever the instructions here tell him to do. And we can sort of represent what he's doing like this. So input goes in, Mr. Computer does something, and then he gives us outputs. And we sort of simplified it to only have one input and output right now. But you can do any number of these inputs or outputs. And yeah, we want to learn how to make these instruction manuals. And one of the most basic instructions that we can give is called a logic gate. All right. And logic gates are actually fundamental to not only programming, but also to electronics and circuits, even math. It's just all connected, which is really cool. And there are a few different logic gates, but the 3 that you'll really need for programming are not, or, and. There are others, but these are really the 3 that you'll need. Just these 3. So logic gates are also known as binary operations or binary functions. And the reason they're called that is because they're used on only the 2 binary numbers, 0 and 1. Remember them? We just learned about them. And we can also think of these as off for 0 and on for 1, or also false for 0 and true for 1. So there's just different ways to think about it, but 0 and 1 are really all we need. They're just different representations of things. And so when we're dealing with logic gates, the inputs and outputs can only be zeros and ones. So inputs and outputs belong to this set. That's what that symbol means. I think Miss B will probably teach you that eventually. No worries to all you latecomers. We're just sort of introducing everything so far, setting things up, as you might say. So we can actually start off with the NOT gate over here, right? And the symbol for a NOT gate looks kind of like this. It's like a little triangle with a circle. And it has exactly one input and one output. And going back to Mr. Computer, when he does something, we can say he's performing an operation or executing a function, right? And what do we know that's an operation or a function? Logic gates, yeah, including NOT gates. That was an awful line. I won't even try that again. But basically, we can move this over here. So instead of just having an abstract do, we can actually take this NOT gate, just move it over here. And this is basically what Mr. Computer is doing, right? Yes. And we can also give the input some name. We can call it A. And a NOT gate is actually also known as an inverter. And that's because what it'll do is take our input, A, and invert it. I know it sounds a little bit obvious, but it'll invert it into the opposite of what it started off as. So A becomes not A. But what does this actually mean? Well, if A is 0, that means that not A will be 1, right? Remember, the inputs and outputs can only be zeros and 1. So if something's not 0, then it has to be 1. Cool. And conversely, if A is 1, then not A is 0, right? It's easy. Oh, I made the line. Okay, perfect. The second one needs a little work, but yay. Cool. So what we just made here is a truth table, and it's just a nice way to show all the possible combinations of inputs and outputs in a system like this. Yeah, it's very much like set theory, and that's why I said sort of logic gates have a lot of connections with like electronics, circuits, math. So in math specifically, like you'll see a lot of concepts that are very similar to set theory. Like even some of the notation is the same. But there are a lot of parallels there. And sort of on these operations, we'll be doing a lot of kind of algebra on them too. We're not going to be going too deep into the math side of this. We're only going to use sort of what we need for programming, which isn't like too deep into it. Okay, so we can also write gates in a few different ways depending on what we're doing or just how we're feeling today. It doesn't matter. So like Miss B said in the chat, a lot of this looks very much like set theory. And so a few different ways that we can write not. Maybe I should move everything over a little bit. There we go. Right, so a few different ways to write not. In coding, you'll see it as not A with an exclamation mark, right? So this is really the one that we'll need. But there are a few different ways, and you don't have to remember these. If anything, remember this one, exclamation mark A. So this will probably be very familiar to anyone who is doing set theory in math. You can call it A prime or A complement. And I know you guys all learned A complements in complementary sets in Miss B's class. So that's sort of your one connection there that you can see. Other ways that you can write it are A with a little hat and also A with a little gun. And this just means It's like a negation symbol for both of these. So all of these mean the same thing. You could also just write it out as not. But yeah, just like if statements. So in coding, this will be what you use in if statements. You don't need to know what they are yet. That'll be next lesson. But just keep in mind that this will become very familiar to you. Okay, so let's sort of say bye to Mr. Computer for a bit as we move on to the next logic gate here. The next one is actually OR, right? And you'll notice that all of these are sort of very basic English words. And so you'll probably have met them a lot in just your day-to-day life. But here's where things start getting a little bit more interesting. An OR gate actually takes two inputs. So it sort of looks like this, but it takes two inputs now. It still has one output, but we're going to add one more input. We'll still have A, but we're also going to add in Miss B. For those of you who haven't been paying attention in Tane's class, don't worry. We're only going to need the first two letters of the alphabet here today. So you can learn the other 24 from her later. Okay, so if you think of OR, A or B is the output. We can keep sort of this table for later, but just remember that this is not. We can make another one for OR here. So this time we have two inputs, A and B, and the output is A or B, right? Great. So you can really imagine this as sort of the same as your day-to-day life. Imagine true and false as telling the truth and telling a lie. So if someone said to you, let's make this a little bit bigger so we can start drawing things out a bit. Let's make it sort of like this. It's a very big logic gate. And then we'll move it down here. Right. So if someone said to you, Aki, that's me, is a dog, or Aki is a cat. Right? So this would be our A input, and this would be our B input. And of course, both statements here are false. And so A and B would be false. So if A is 0 and B is 0, then A or B is false. This part is probably pretty intuitive for a lot of you. And of course, if we change one of these, so if we say Aki is a dog for A still, but we say or Aki is a robot. So obviously A is still false. Aki is not a dog, but Aki is a robot. And so since one of these things is true, then that means the entire statement is true, right? So Aki is not a dog. Aki is a robot. And so A or B is true, right? So if I say Aki is a dog or Aki is a robot, then since one of these is true, both of these are true. Okay. And the same works the other way around. So if I switch around A and B, if I move this down here and make the first statement, Aki is a robot, and the second statement, Aki is a dog, we've basically just swapped the position of this, right? So intuitively, we know Aki is a robot, yes. Aki is not a dog. And so A or B is still true. And then this is true as well. And of course, if both statements are true, like Aki is a robot and Aki is tall, right? Okay, fine. Aki is short. Then A and B are both true, and A or B, there should be one, is true. The entire sentence is true if at least one of the inputs is true. So that's an OR gate. You'll also see OR written in a number of different ways. Let me put this as a table first. OR can be written as A pipe B. So it's like a little vertical line. You'll see this one in programming a lot. Especially in programming, you'll see 2 bars here. And you don't need to worry about that now, but this is probably the most common one you'll see. I'll explain why once we get there. But other ways that you can write it are A and, or B with the little caret. So this is like set notation now. A union B, right? And also A plus B. So union, if you think about it, is like in the set of A and B, anything in A or B is true. And why do we have A plus B in here? Well, if we look at the truth table, it sort of resembles addition a lot, doesn't it? 0 plus 0 equals 0. 0 plus 1 equals 1. 1 plus 0 equals 1. But what about 1 plus 1? So for those of you who are good at math, 1 plus 1 is slightly different from what we know. But remember, the output can only be 0 or 1. We can't actually go over 1. 1 is the maximum, and we've already reached the cap. So in this case, yes, 1 plus 1 equals 1, right? Okay, what about and? Let's get rid of this. What about and? And sort of looks like this. It's like the or, but we flattened it out a little bit. And it's a little bit more strict in that we can't tell half-truths anymore. If I say Aki is tall and Aki is short, A and B, then A and B is obviously false because both these things can't be true at the same time. Which means an and sentence is only true if both statements are true, which means neither of these statements can be a lie, right? And so and can be written like this. The table A, B, A, and B. So obviously if we have A is false and B is false, then both are just false. We can get rid of this part over here. If A is false and B is true, so if Aki is tall and Aki is a robot, that's still false, right? And same goes the other way around. But the only time that A and B is true as a sentence is when A is true and B is true at the same time. And since OR was sort of addition, we can liken this to multiplication. You can see like 0 times anything is 0. 0 times 1 is 0. And 1 times anything is that number, which is 1. But yeah, and can also be written in a few different ways. This is the one you'll normally see in code, A and B. It's very intuitive because the word is exactly like, it uses the and symbol, so the ampersand here. In code, the same thing as or, you'll see two ands, so A and B is what you'll see in code. And that's basically just called a short circuit. It means that if it finds that one of them is false already, it won't even go on to the next input. So it won't check what B is if it knows that, hey, A is already 0, so we know that this whole sentence is going to be false. And so other ways you can see it written are very much same as and, but just the opposite. So in Boolean logic, you'll see A with the little wedge, but downwards. B, this is A and B. All of these are read A and B. It's just different symbols to represent the same things. Oh, my head is blocking the table. I'm sorry. Let me move this all over. My head is too big. Life is easier when you're just software. All right. And then same with set theory, we can write A intersects B, right? So if we go back to the math example, if we have two circles of A and one is B, then A and B is only the parts that intersect or that A have in common with B. So if it's 1, then B has to be 1 here as well. And as I said, this is A times B is a good representation of and. You can also write this as AB. You can also write it as A times B like this, but the reason we don't like to use this a lot in I guess engineering and other subjects is because X is also the symbol for cross product, which is something completely different from multiplication. So yeah, you can write this, but in different contexts, it can get really confusing. And we want to be as clear as possible, especially if we're talking to a computer. Not that you can type sort of these into code. Really, you only need this column. You can just ignore all of these, but they're good to know. If you ever see them in other contexts, like if you do Boolean algebra, those are sort of really useful that way. And so there are a few different simplification rules that we can use for these. We don't have to prove them, but I'm going to list them out for you. Yes, the difference sometimes is uppercase X. It is a little bit hard to sort of differentiate sometimes too, especially if you have X as a variable as well. It's a little bit better just to be like super clear about this. Yeah, math has a lot of different symbols. So does programming, but also math. Like if you look at derivatives, like there's some symbols that just uses this as a derivative. And you can keep going with adding more dots. And it gets really hard to see if it's written down. I'm not going to go too deep into Boolean algebra, so you don't need to worry about that. I'm just going to list out the simplification rules for you, just so you're aware that they exist and that you know that they're sort of available to you. So these are sort of just tools that you can use to simplify logic in your code. So one thing that you really want in your code is to be sort of very efficient, right? So you don't want to have a bunch of statements that do the same thing, essentially. If you can have one sentence to do something, why would you want like 10 to do it, right? Yes, X's are all different symbols. Miss B is fluent in Greek. We use a lot of those in math. In addition to Latin characters. So that's always fun when you have both of those of the same variance in the same equations. All right. So over here, we have not A equals A, right? And this is sort of very intuitive. Like if you say that if you have not A, then obviously like if you say not A, then these two nots cancel out, right? So a lot of these rules are fairly simple. It does get really complicated if you do like very, very long-winded equations, very complex equations that you need to simplify. For programming, I'd say you don't really need those to get started. Like they're definitely helpful to know, but really like it's good practice. You don't have to do it. And I know this kind of looks a little bit intimidating, so we're not going to delve too deep into it. They're just sort of nice to have, useful to know. And you can become a very good programmer with these, but again, not necessary right now. So A or 0. Now, what does this mean? A or 0. So if you add a 0 to anything, right? If you think of this as addition, it's also just A, because you know that as long as one thing in A is true, then A is true. And if A is already 0, then adding another 0 as an OR doesn't do anything to A. So A plus 0 is A. Now, A plus 1 is a little bit different here. A plus 1 equals, let's take a look. If A is 0, then 0 plus 1 is 1, right? If A is 1, then 1 plus 1 is 1. So A plus 1 is always 1. All right. What about and? Let's see. A times 0. Now, what did we say? If we have any statements that are false in an and statement, that makes the entire statement false, right? Anything times 0 is 0. So A times 0 is 0. And A times 1 is very much the same thing. Like all of this transfers from math. So you don't really need to learn anything new. Even though it's representing something different, it's really the same way of looking at it. And a lot of things in programming and in math will be like that. They're very interchangeable. Even if they're not talking about the same things, we use many of the same tools, and we sort of interact with them the same way. So A times 1 is just A, right? A little bit of a harder thing is something called De Morgan's law, but this is really the most advanced thing that we're going to get into today. So De Morgan's law, write it out for you, but you don't really need to know the name of this. De Morgan's law is saying if you have A times B and you not everything, right? This is kind of like mathematical expansion. You'd think that you'd be able to distribute not, right? Wrong. That's not how it actually works. So if you actually do out the logic tables, which we probably don't need to, it's a good exercise for y'all at home if that's something you're interested in. But we know that not A times B, or A and B, I should say, is not A plus not B. Kind of works out this way instead. It does sound like a D&D character. De Morgan. It's like StarCraft. Anyway, the opposite is also true. So not A or B equals not A times not B, or and not B. And I say equals, but yeah, it really just means that their outputs are exactly the same. That's another way to think about it. So the more you think about this as how it applies to computers, I think the easier it'll be when you learn programming. Okay, so now that we know these three logic gates, not, or, and, what do we do with them? Where is this going? How do we use them to code? And when can we play Minecraft? So logic gates are actually at the basis of how computers work. And using them, we can write instructions for computers, right? Remember the instruction manual we had for Mr. Computer. So we're actually the ones writing it now. And using them, like, we can get the computer to understand what we're asking of them and to get them to do what we want them to do. And we have to be very specific in this way, in the form of conditional statements and loops in our program. So conditions, obviously, they mean like, if something happens, then do this, right? And loops are kind of like, do the same thing over and over until something happens. So we're going to kind of start delving deeper into these in our next lesson. So this is like a conditional. And these are like the fundamentals of what make up code loop. And there are like different types of loops. Like you can have loops with different conditions. So it's sort of like nested in here. So you use conditions to sort of tell the computer like when to keep going and what to keep doing within the loop, right? And so that's sort of the connection there with where this works with code. So this is incidentally probably our next lesson. So where does Minecraft come in? Well, let's open up Minecraft. So Minecraft is kind of interesting because it has all these components, and it has all the components that we need to implement these 3 logic gates that we learned, and also other logic gates, but mostly these 3. And you can actually build very advanced circuits in Minecraft if you wanted to. Like, you could build a computer, for example. So our dear TAJ is going to hop on and show us how to apply what we just learned to a keycard diamond dispenser. It's not a full computer, but those take years to build, and this is only our first lesson. But this is almost as good, and we don't need to wait around to buy a 3080. So I'm going to join Jay in Discord over here. What's up, Jay?
Hello.
Hello.
You guys are ready to learn how to build some programs, but in Minecraft?
Aye, aye, Captain.
Alright, so the first thing we're going to teach, in Minecraft at least, is how to do these logic gates. And especially in Minecraft, it's slightly different because you don't have as many complicated components as you do on a digital circuit board. So in Minecraft, you actually they have 2 fundamental components that everyone needs to use to be able to do anything redstone related. And that's the inverter or NOT gate and the OR gate, actually. Minecraft basically fundamentally only has 2 logic gates. And I can show you right here. The inverter, I think everybody knows. It's if you have any sort of output, and then you put say like a button on one end, or even let me grab a lever because that's easier to use. So you have a lever, right? This is right now is off. You can see on the other side by putting a redstone torch on the other side of the block, it's already on. So right now the position of the lever, the input, is off, but your output's on. And if you turn the input on, it turns off the redstone torch, and now your output is off. This is a logic gate NOT. Essentially, it just inverts whatever input you have. So that's the first one. The second one is just as easy to kind of intuitively make in Minecraft. You've probably done it already. If you have, let's say, this is your output, you can put like put a glowstone or a lamp. Here's a lamp, right? And we have 2 inputs. This is an OR gate, because whatever you turn on, even if you turn on both at the same time, it's going to light up that lamp. This is pretty intuitive. If you've played Minecraft, you try to use any basic redstone, you've basically seen the OR gate. And you can extend that as long as you want with redstone repeaters or anything else that can extend a signal. The one difference in Minecraft is kind of just like real world circuits. You actually do have circuit propagation. So like redstone has a limit. You can put like 15 redstone pieces together, and then I think that's the limit. Any farther than that, it won't detect a signal. So you kind of need to extend the signal out. But because we have the ability to extend the signal, it's not really an issue. You can kind of think of it as like a high and a low, or a 1 and a 0. So there's that. Let me just fill up this sand because it's bugging me. Alright, so using those two logic gates, the NOT and the OR, we can pretty much make every other logic gate possible. So one of the most basic ones is the AND gate. And the AND gate is kind of, it's using a system of 2 inverters, and then actually another inverter here, and then you put 2 switches. So you have your A input and your B input, and you can see once you flip one of the switches, it inverts the torch here, but the other one stays on, and then it turns off the final output. So this, as long as one of them is off, or both of them are off, the entire thing is off. But if you turn both on, then the output is on. And this is essentially just 3 knots tied together with some redstone. You can see like there's 3 redstone torches, which is basically 3 inverters. That's how you make an AND gate. If you want to make a NAND gate, which is just you put an extra knot at the end, just take off this torch, and then you have a NAND gate, which is just you invert all of your all of your outputs. So as long as they're both on, then the output is off. So with these kind of components, we can build a lot of fancy machines and stuff that basically do programming logic, but in a Minecraft environment. So as you can see for this one, I have a machine here that if you supply this dropper with the correct keycard, and the box containing the diamonds in the back has a sufficient supply, then it'll give you some diamonds. So I'm going to get you guys, or I'm going to show off this by giving Aki a keycard. So you can go ahead and put it in that dispenser over there on the left. Now you gotta right click it.
No.
Oh no, the button's gone.
No, my button.
There, just no, right click the box, not the button.
Alright.
Put it in, yeah, and then click the button.
Now we click the button.
Oh, there's a diamond. So because the box in the back had enough diamonds, it'll give you one. If you just keep pressing it with the keycard inside, eventually this thing is not going to have any it's going to say that, yeah, so I think at this point there's not enough diamonds in the box, or at least there's a low amount of diamonds in the box, so this machine will not dispense any more diamonds, given that keycard. And if we take a look in the back here, so if you just come around here, I won't go into super detail about what these complicated Minecraft contraptions are, because these are kind of, you can Google it. So this is a keycard reader. You can kind of look up how to do that in Minecraft. The circuitry for that is not necessarily logic gate based. It's more so that it's just Minecraft's game mechanics allow you to do kind of things like that. There's a lot of hacky things you can do with Minecraft's game mechanics that let you build kind of weird contraptions that do things. So this on the left side is a my left side is a keycard reader, and then this thing on the right is a automated dispenser. So if the dispenser spits an object, it'll just spit it out immediately. And then here we have this box full of diamonds. If you take a look inside the box, you'll see that there's still diamonds in there. Right now it's set up so that if it sees that there is 1 stack of diamonds plus 60 diamonds, that is the limit of how many. If it has any more than that, it'll give you diamonds. If it has that amount or less, it'll refuse to give you diamonds. This is using a redstone comparator. I can point to it here. But the main logic part of this is we want the two things to interact together. So we want the keycard reader to work only if the box has enough diamonds. So that's where this AND gate actually comes into play. You can see this one's actually a NAND gate because to turn off a hopper, you have to invert the signal. So like a redstone on signal will disable a hopper. So this is a NAND gate. So if you can think of it as if the keycard reader has the correct keycard and the box has enough diamonds, then this signal will turn the hopper on. And that is one of the fundamental ways you can use kind of logic gates, even in Minecraft, to kind of program simple things. This essentially is a program. You give it an input, which is the keycard. It has an external input as well, which is the box of diamonds. If both conditions are satisfied, then the output happens, which is literally an output of diamonds.
Nice.
So that's like kind of the first thing you can kind of do in Minecraft. There's a little bit more fancy stuff here. This is a SR latch, which in digital circuits is what we call a set reset latch. In Minecraft, you kind of think of it as like a toggle. So like if I want to turn on the light on the right, I press the button on the left. If I want to turn on the light on the left, I press the button on the right. That kind of traditional circuitry for a set reset latch is that the button kind of corresponds. So the reset kind of turns on the opposite side. But if you want to build it kind of in a more Minecraft sense, here's the kind of Minecraft abusive way. This is not a real logic gate per se, but it is a way that you can use Minecraft mechanics to imitate the same kind of latch. This one is more intuitive, that the set button will turn on the correct light that's like right in front of it, and then the reset will turn on the light that's right in front of it. So this is just the same as this one, but inverted. The reason why you'd kind of want to make this sort of thing in Minecraft is maybe you want, I don't know, to turn on a set of hidden doors from one side, but then not have it enable from the other side until you press it again to open it from the other side. You can do a lot of cool things with this. So say you want to, I don't know, collect some sort of farming material from one end of a railroad, and then you want to go to the other end, press the button. It essentially is a lever, but you can control the lever without a lever by just using two buttons. And then there's a lot of other fancy things you can do, like you can build a, what is it called? Like a flip-flop, which is essentially a machine that basically lets you turn on and off something, but with a constant redstone input and output with a button. So I'm not going to build that right now, but there's a lot of fancy things you can do just in Minecraft with these basic logic gates. So coming up, we're probably going to have an office hour. And in the office hour, we're going to do some cool things and maybe bring you guys on to kind of try out your own things in Minecraft. We can do some like interactive demos or hands-on things with Minecraft that you guys might want to try out. But yeah, this is kind of just like a preview of what you can do with the logic gates that you've just learned today in something practical right away, which is Minecraft.
Yay. Thanks, Jay. Everyone give a round of applause for Jay. We won't be able to hear it, but he appreciates it nonetheless. So there are a few things that Jay brought up that we didn't completely learn in the lesson. So one of them is the NAND gate. And that's basically an AND, but with a NOT at the very output of it. So it's basically just the exact opposite of an AND. And you saw that he actually had to build an AND gate within Minecraft out of the different components like ores and inverters. And that's because Minecraft sort of doesn't have an exact, I guess, one-to-one gate or component that represents AND. And so that's something that you can do. If you have ores and inverters, you can actually just make other gates as well. So there are a few other gates that we didn't go over. If there's interest, during office hours. I can go over those, especially if you want to actually make Minecraft builds. So I know that this is a much more visual way of programming, but it's really good to sort of get the concepts you need for programming. And it actually really does help to start doing your own builds, because then you can see like what different inputs do and what the components actually are doing to the inputs. And it makes it a lot easier to sort of like wrap your head around that. But yeah, yay. Thank you for all the applause for Jay. I am going to try to set up a server with Jay where we can have like a creative mode sort of server with just flat map, flatland, I guess. So that's coming up this Saturday. I'll tweet it out if anyone wants to see it just beforehand. We're probably going to reset it every once in a while, so don't put anything on there that you really like, but it's mostly just a sandbox for you to play around. During the office hours, feel free to ask us any questions. Like, we'll come onto the server and we can just all sort of see each other's creations. It'd kind of be fun to do like maybe even like a show and tell or something. We'll go around just to take a look at things, or just to help out with your circuit if it's not really doing what you intended it to do. But yeah, we'll probably also, maybe we'll give more demos too in the office hours, but it's pretty flexible. But yeah, that was your first CS lesson. And I know that we haven't touched any code yet, and we are going to, don't worry. It's always good to sort of get these concepts in your head first before diving into code. But once you see these, like, you're going to go, oh, I know these already. So it'll be really easy for you to pick up. But yeah, survival programming server, just like real university. We can do that too at some point. See if the creepers like our builds. But yeah, thanks for tuning in, guys, to lesson 1. Lessons on Wednesdays as usual, and office hours will be Saturday at probably around the same time, 7 p.m. Yeah, make sure to follow us at Spirit Uni on Twitter. Like and subscribe, as they say. Ring that notification bell. Yeah, I'll catch you guys on Saturday.